Hello everyone. So today we shall see the inverse Z transforms. So we have been taking the Z transform the discrete time signal system. So given the x of n, how we have computed the x of Z. Now by the inverse Z transform is that given the representation, some representation of x of Z with its ROC, then we need to compute x of n. So often this analysis involves finding the Z transform of sequences and after some manipulations of the algebraic expressions for finding the inverse Z transform. The inverse Z transform is basically computed by the this following complex contour integral as x of n 1 upon 2 pi j x of z to the power n minus 1 dz, where your this integral is not the regular integral you often encounter with the real valued functions, and because this x of z is a complex valued function, so this c represent a closed contour within the ROC of the z transform. Okay. So this integral expression you can derive by using the Cauchy integral theorem from the theory of complex variables, but we won't dwell into those complex mathematics. But for computing the inverse Z transforms, we will use the less formal procedures, which would be sufficient and preferable to techniques in comparison to computing the inverse Z transform using this equation. Okay, so there are many methods, but the most important method which we will be seeing in this course is based upon the partial fraction expansion. Okay, so let's assume that x of z is represented by a ratio of polynomials like we had seen earlier, say from k is equal to 0 to n bk z minus k 0 to n ak z minus k. Okay, so this is the ratio of polynomials in Z inverse, which arise quite frequently when you are doing the analysis of LTI systems. So I can represent this above equation in this expression is by taking the z to the power n common factor from k is equal to 0 to m bk z n minus k and z to the power n k is 0 to n ak z n minus k. Okay, so in this representation it is quite clear that you have m number of zeros and n number of poles at non-zero location in the finite z plane. Okay, where we have assumed that a0, b0 and an and bn are non-zero. Okay, now if you have m greater than n, then in that case you would have m minus n number of poles at z is equal to 0. This you can see from this formula. On the other hand, if you have n greater than m, then you would have n minus m number of zeros at z is equal to 0. While you would see that there are no poles and zeros at z is equal to infinity. Now another thing is you can compute the inverse Z transform by the power series expansion, which is also quite powerful method. We have seen that you compute x of z as summation over n minus infinity to infinity xn z to the power minus n. Okay, so on the right hand side you would see that this is nothing but a Lorentz series. Where the sequence values x of n are the coefficients, these are the coefficients of z to the power minus n. Meaning to say, you can write this expression as some terms plus x to the power minus 2 z square plus x minus 1 z 0 plus x1 z inverse plus x2 z minus 2, all the terms. So it becomes a series, what we call the Lorentz series, where the sequence values x of n are the coefficients of z to the power minus n. So we can take a quick example to illustrate what we actually want to do. Say for example, we are given x of z as z square 1 minus 1 by 2 z minus 1, 1 plus z minus 1 and 1 minus z minus 1. Okay, so first of all, this is a rational function. Another thing, that partial fraction expansion may not be appropriate to compute the inverse Z transform, since you have the only pole at Z is equal to 0. So in such cases, we can use this power series expansion method, where if I simplify this above expression, I would get z square minus 1 by 2z minus 1 plus 1 by 2 z of minus 1, right? So you would have your x n as, when you have n is equal to minus 2, the sequence value or the coefficient is 1 at n is equal to minus 2. For n is equal to minus 1, you have minus 1 by 2. For n is equal to 0, you have minus 1. Now for n is equal to 1, you have 1 by 2, and it's 0 otherwise. Right? So this expression can be equivalently written as x of n as, by using the unit impulse functions, as del n plus 2 minus 1 by 2 del n plus 1 minus del of n and plus of 1 by 2 del n minus 1. Okay, so this would be the sequence. So in a similar way, by using this expansion method or power series expansion method, you can compute the inverse Z transform for many transcendental functions such as logarithmic, sinusoidal, hyperbolic sinusoidal, etc. We can take a quick example of the logarithmic function. Let's say 1 by z is equal to log 1 plus a z inverse, where you have the ROC as mod of z greater than mod of a. Okay, so for this we can use the Taylor series expansion for the term Taylor series expansion for the term log 1 plus x, where mod of x is less than 1. Right? So on taking the Taylor series expansion, you would get on the right hand side as for from n1 to infinity, you have minus 1 to the power n plus 1 a n z minus n divided by n. Right? So you have x of n as minus 1 to the power n plus 1 a n over n for n greater than equal to 1, 0 for n less than 0. So for the logarithmic function, this is how you can compute the inverse Z transform using the power series expansion. Okay, so these are the two powerful methods for computing the inverse Z transform. First we had seen the partial fraction expansion, and the second one is the power series expansion. So now we can discuss about the Z transform properties, which are mostly similar to the properties we have discussed for the discrete time Fourier transforms. Note that in the last class we discussed the properties of the ROC of the Z transforms, right? So the first so let's say we have x of n, which we will represent in this form, that the Z transform, the inverse Z transform, both side is x of z, and its ROC is some R of x region in the complex plane. So the first property of linearity says that if I have x of n as its Z transform as x1 of z with ROC as Rx1, and x2 of n with Z transform x2 of z with its ROC as Rx2, then by combining the principle of superposition or the additivity or homogeneity, I will write directly as ax1 of n plus bx2 of n its Z transform. So if I have this sequence on the left hand side, then it would have the Z transform as ax1 of z plus bx2 of z. Okay, and this ROC contains the region which is the intersection of both these regions, Rx1 and Rx2. So this operator is the set intersection operator. Okay, so there are some couple of important points, because since two rational functions would be added if I have the the sequence as this one, the summation of two different sequences. So it might be possible that you may notice some pole zero cancellations. So for sequences with rational Z transforms, so if the poles of ax1 and if the poles of ax1 plus bx2 consist of all the poles of x1 and x2z, that is, if there is no pole zero cancellation, then the ROC will be exactly equal to the overlap of the individual ROCs. Okay. Now, secondly, if this linear combination is such that some zeros are introduced that cancel the poles, then the ROC may be a bit larger. Okay, so be careful while computing the region of convergence for this linear combination when you have the pole zero cancellation particularly. So for example, you have x1 of n and x2 of n, both are of a infinite duration sequences. Okay, but their linear combination, say for example you get, is of finite duration, and we know from the properties of the ROC that for the finite duration sequences, the ROC is the entire Z plane with the possible expansion of Z is equal to 0 or Z is equal to infinity. Okay. Say you have x of n as a to the power n u1 minus un minus n. Okay, so both these, if I write this sequence as the summation of two sequences or the linear combination of two sequences, so you will notice that this part and this part are of infinite duration, with the ROC mod of z greater than mod of a. Okay? But the z transform of this sequence has a pole at z is equal to a. You can compute its z transform, and this pole is cancelled by a 0 at z is equal to a, which appears due to the linear combination of these two things. So the ROC is the entire z plane except z is equal to 0. Okay. Second property is the time shifting. Which says that if I shift the sequence by n naught number of samples, then while computing the z transform, this additional term is introduced. It is z to the power minus z to the power minus n naught, while the ROC would remain the same as the earlier, except for the possible addition or deletion of z is equal to 0 or z is equal to infinity, right? Because you have 1z to the power minus n naught introduced in the x of z. So there, so depending on this n naught, we can see whether the sequence is shifted to the right or to the left. So if you have n naught greater than 0, then your xn is shifted right. If you have n naught less than 0, then your xn is shifted left. And as I mentioned, that the ROC can be changed, since the fraction, since the term z to the power minus n naught can alter the number of poles at z is equal to 0 or z is equal to infinity. Right? Just keep this thing in mind while computing the ROC for the shifted sequence. The next property is multiplication. By an exponential sequence. So what I mean to say, that if you have this xn and I multiply it some exponential sequence z to the power xn, then its z transform would change by z over z naught. So you need to replace the z by z over z naught in the expression of the z transform, and the ROC of this sequence would be mod of z naught Rx. Right? It means that the ROC is in fact scaled by this number z naught. For example, if you consider the region of convergence as some annulus mod of z lying between RR and RL, then this mod z Rx would be mod of z is mod of z RR and mod of z naught RL. Okay, so this would be the region of convergence for some annulus. The next property is the differentiation of x of z, meaning to say that if I have the sequence x of n and I multiply that sequence by n, then the z transform would be minus z times the derivative of that z transform with respect to z, where the ROC would remain the same as Rx. Okay, we can quickly see the sketch of the proof of this property. Then we are given with this x of z, which is computed as minus infinity to infinity, x of n z to the power minus n. So if I take the derivative on the left hand side by and multiply by minus z, so minus z dx by dz. So on the right hand side it will give me minus n x n z to the power minus n minus 1. Okay, which I can simplify to summation over n x n z to the power minus n, which is nothing but your z transform of n x n. Okay, so this property you can see to compute the inverse z transform of the logarithmic function which we had seen earlier. Say for example, you are given this x of z as log 1 plus a z inverse for mod c greater than mod a. So if I take the derivative of this logarithmic function, would give me a z to the power minus 2 1 plus a z minus 1. Okay. So n x n z transform by using this property, which is minus z dx by dz, and minus z dx by dz, seeing this expression, is nothing but az minus 1 plus az minus, because this minus 2 would, one of this z would appear here. Okay. For mod z greater than mod a. So the inverse transform can be obtained by the combined use of linearity and time shifting property now, which says that nxn would be equal to a minus a to the power n minus 1 u n minus 1. So if I write x of n is minus 1 to the power n plus 1 in u n minus 1, whose z transform would now be equal to, in fact, logarithmic of 1 plus a z inverse, where the ROC would remain the same, right? So you can use this differentiation property to simplify this logarithmic term or some transcendental functions wherever applicable, and then using the other properties like linearity and time shifting property, you can directly compute the inverse Z transform also. The next property is conjugation of a complex sequence. Which says that if you have, if I take the complex conjugate of any sequence, then its Z transform would change to the complex conjugate of that function with Z changing to its complex conjugate as well, while ROC would remain the same as Rx. Okay, next property is time reversal. So all these properties you can prove by yourself as well by simple manipulations in the Z transform function, like we had seen one of the quick sketch of the proof in the earlier property. Now if I have the time reversal as x star of minus n, then the Z transform would change to x star 1 by z star, okay, where the ROC would change to 1 by Rx. Okay, so 1 by Rx implies that Rx is inverted, meaning to say, so if you have the annulus as if R of x, RR lying between mod of z, RL, then 1 by Rx implies that mod of z lie between 1 over RL by 1 over RR. Okay, so this is what it means by the inversion of Rx. The last property is the convolution of sequence, which you would mostly see when you are dealing with the LTI systems, or for computing the response of the LTI system for some input. So if you have two sequences convolved with each other x2 of n, then the Z transform would become x1 of Z multiplied by x2 of Z with the ROC again as the intersection of Rx1 and Rx2. Okay, so we can see quickly all the properties which are tabulated here. So this table I have borrowed from the book OpenN, Discrete Time Signal Processing. So here you can see that for if the sequence has x of n with its transform as x of z and having ROC as Rx1, then the linear combination, which is the linearity, contains this Rx1 intersection with Rx2. This is the time shifting. This is the multiplication by the exponential sequence. This is the derivative property, the complex conjugate property, time reversal, and the convolution. Okay, so all these properties are summarized in this table, which you can refer and use it to compute the inverse Z transform or the Z transform and their respective ROCs. Okay.